Stars die, we know that, but how they die determines everything. The flash that outshines a billion suns, the elements forged in seconds, the remnants left behind. You think a supernova is just a star exploding? That is wrong. There are types, categories, mechanisms so different that calling them all supernovae is like calling a firecracker and a nuclear bomb the same thing. Some leave neutron stars, others black holes. A few leave nothing at all. The universe has 8 major ways to tear a star apart. Each one writes its own signature across space-time. Let me show you what really happens when stars collapse. If you value documented astronomical discovery and cutting-edge supernova science like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual, using sources from Nature Astronomy, published June 2021, on electron capture supernovae. From Astronomy and Astrophysics, published March 2025, analyzing 107 hydrogen-rich superluminous events from the Zwicky Transient Facility. And from Monthly Notices of the Royal Astronomical Society, published September 2024, modeling the cosmic rate of pair instability explosions. These are deep papers from the peer-reviewed literature that astrophysicists actually read. Not press releases, not Wikipedia summaries, the real data. Now back to the information. Type IIa, thermonuclear detonation. This is not a massive star dying. This is a white dwarf that reached 1.4 solar masses and went critical. Carbon and oxygen ignite everywhere at once. The entire star burns in seconds. No remnant. Just expanding debris moving at 10,000 kilometers per second. Every type Ia peaks at roughly the same brightness. That makes them cosmic measuring sticks. Astronomers use them to map the expanding universe. In 1998, observations of distant type Ia supernovae proved the universe is accelerating. Dark energy. The Nobel Prize followed in 2011. The standard scenario runs like this. A white dwarf in a binary system pulls matter from a companion star. Could be a red giant. Could be another white dwarf. Material piles onto the surface. Hydrogen at first, then helium. Pressure builds. Temperature climbs. When the white dwarf hits 1.4 solar masses, the Kendra-Sekar limit, its carbon-oxygen core reaches critical density, 2 times 10 to the 9th grams per cubic centimeter. Nuclear fusion ignites, but cannot stabilize. The entire star detonates. Astronomers detected 1,533 type Ia events in 2024 alone, according to the Rochester Supernova Catalog published January 2025. But not all type Ia explosions are identical. Some are overluminous. Type Ia-91. T-like events shine brighter than standard. They likely come from more massive progenitors or different ignition conditions. Some are subluminous. Type Ia-91 BG-like supernovae are faint and fast declining. They probably detonate at lower masses or with incomplete burning. Then there is type Ia-02 CX, extremely weak explosions. They might be partial detonations where the white dwarf survives, just wounded, not destroyed. Astronomers found 5 type Ia-02 CX events in 2024. Rare. Fascinating. Silicon lines dominate the spectrum. That 6,155 angstrom absorption feature is the signature. No hydrogen. No helium in most cases. Just ionized silicon and iron group elements. The light curve rises fast, peaks in about 19 days, then declines following the radioactive decay of nickel-56 into cobalt-56 into iron-56. That decay chain powers the visible glow for months. Supernova 2011 FA in the Pinwheel Galaxy. Just 23 million light-years away, one of the closest type Ia events in decades. Detected on August 24, 2011. Spectra taken within hours. Every observatory on Earth pointed at it, every wavelength monitored. The data confirmed the standard single degenerate model, a white dwarf accreting from a companion. The detection rate for type Ia is roughly 1 per century per galaxy, but we monitor millions of galaxies now. The numbers pile up. Type IB and type Ike, stripped envelope core collapse supernovae. These come from massive stars that lost their outer hydrogen layers before exploding, 25 solar masses or more. Strong stellar winds ripped away the envelope, or a binary companion pulled it off. When the core runs out of fuel, it collapses. The rebound blasts the remaining helium and heavy element shell into space, velocities exceeding 10,000 kilometers per second, kinetic energy around 10 to the 51 ergs. Type IB shows helium lines in the spectrum. Type IC does not. Both lack hydrogen. Both show broad features indicating high expansion speeds. The progenitors are likely Wolf-Rayet stars or stars in interacting binary systems. These objects are hydrogen-free before death. Supernova, 1994. I was the prototype type IC. Discovered in the Whirlpool Galaxy. Spectrum showed oxygen, calcium, iron, no hydrogen, no helium. The light curve resembled type Ia, but the spectrum did not match. Astronomers detected 43 type IB and 70 type IK supernovae in 2024. The strip process varies. Some stars lose just hydrogen, others shed hydrogen and helium both. The mass loss mechanism determines the subtype. Binary interaction is efficient. Winds are less so, but rotation matters. Fast spinning stars develop stronger winds. They lose mass faster. The final core mass at collapse determines the remnant, neutron star or black hole, type Tsutsune. The classic core collapse supernova, massive star, 8 to 50 solar masses. Hydrogen envelope intact. Iron core forms at the center. Fusion stops, pressure drops. Core collapses in less than 1 second. Density shoots to nuclear levels. Neutrons form. The core rebounds. A shock wave races outward. Hydrogen-rich layers explode. Peak luminosity around 10 to the 43 ergs per second. The light curve shows a characteristic plateau. That is type 2P. The plateau lasts 50 to 100 days, then declines following nickel decay. Type 2, L lacks the plateau. Linear decline from peak, probably less hydrogen in the envelope. Type 2 is Nabi, starts with hydrogen lines that fade. Helium lines emerge. The star lost most, but not all of its hydrogen before exploding. Supernova, 1993 J in Messier 81 was the type 2b prototype. The 2024 statistics show 52 type 2.1, 25 type 2IP, 40 type 2b detected. According to Rochester data, published January 2025, Supernova, 2023, I was Esfin Messier 101, discovered May 19th, 2023. Just 21 million light years away, one of the nearest type 2 events in years. Spectra revealed a red supergiant progenitor. Pre-explosion images from Hubble confirmed it. Estimated mass around 10 to 12 solar masses. The X-ray and radio emission from SN 2023 IXF reached 3 times 10 to the 40 ergs per second, according to research published in Archives in October 2024. The brightest hydrogen-rich supernova on record in those wavelengths. That emission comes from the shock wave hitting dense circumstellar material. The star was ejecting mass before it died. Winds, pulsations, something unstable. Type 2 shows narrow hydrogen emission lines. The N stands for narrow. These are supernovae interacting with dense circumstellar shells. The progenitor star shed massive amounts of matter in the years before collapse. When the explosion hits that material, intense shock interaction creates the narrow lines. The CSM is moving slowly, a few hundred kilometers per second. The supernova ejecta moves at 10,000. The collision is violent, luminous. Long-lasting, some type 2 events become superluminous. They cross into SLSN-O2 territory, sustained by CSM interaction. The mechanism is not radioactive decay. It is kinetic energy converted to light by shocks. Efficiency is high. These explosions can shine for years. Type 2 events are rare. Only 52 detected in 2024, but they are crucial. They show us that massive stars are unstable before death. They lose mass eruptively. Something triggers that mass loss. Pulsational pair instability, perhaps. Wave-driven mass ejection. The physical mechanism remains debated. Superluminous supernovae. SLSNI and SLSN2. Events with peak absolute magnitudes brighter than -20. Some reach -23, 100 times more luminous than standard supernovae. They require extreme power sources. Radioactive decay cannot explain them. The nickel mass would be absurd. SLSNI are hydrogen poor. They show spectra similar to type IK, but far more luminous. The power source is likely a magnidar. A neutron star spinning at millisecond periods with magnetic fields 10 to the 15 Gauss. As it spins down, rotational energy pumps into the ejecta. Models predict light curves matching observations. The rise is slow, the peak bright. The decline stretched. Supernova. 2024 AFAV demonstrated this. Discovered in early 2024, light curve showed periodic modulations. The period decreased over time. A chirp signal. Researchers published analysis in September 2025 in Archives showing that Lenzi-Thirring precession from a tilted accretion disk around the newborn magnetar explains the data. The magnetar forms. An accretion disk tilts. Frame dragging from general relativity causes precession. The precession rate changes as the disk evolves. That creates the chirp, first direct evidence of the lens-thirring effect in a young supernova. SLSN2 are hydrogen-rich. They arise from circumstellar material interaction. The progenitor loses huge amounts of mass. The supernova slams into it. Shock interaction powers the luminosity. Research published in Astronomy and Astrophysics in March 2025 analyzed 107 SLSN2 events from Zwicky Transient Facility. Peak magnitudes ranged from -19 to -22. Rise times varied from 30 to 150 days. The diversity suggests different CSM morphologies: dense shells, extended winds, clumpy structures. Supernova 2023 GPW showed this complexity. Published analysis in Archives in September 2025. The light curve displayed an abrupt drop around 180 days post-peak, unprecedented for SLSN2. Spectra showed early flash features. High-velocity photosphere? UV excess from interaction. The CSM was dense and confined. Then the forward shock reached the outer edge. Interaction ceased. Luminosity dropped. The star had ejected that material less than a year before exploding. Eruptive mass loss. Pulsations. Instability. The host galaxies matter. SLSN hosts are low mass, subsolar metallicity, high specific star formation rates. Research published in Monthly Notices in July 2023 showed metallicity is more important than star formation. Low metal content allows massive stars to retain angular momentum. Fast rotation enables strong magnetic fields. Magnetars form more easily. Pair instability supernovae, PISN. The most extreme explosion mechanism, stars with helium cores between 65 and 130 solar masses reach core temperatures above 700 million Kelvin. Photons gain enough energy to spontaneously create electron-positron pairs. Pair production removes photon pressure, supporting the core. The core contracts. Temperature spikes. Oxygen and silicon ignite explosively. The energy release exceeds the binding energy. The entire star disrupts. No remnant, no black hole, just expanding debris carrying up to 100 solar masses of ejected material. The radioactive nickel yield can reach 20 solar masses, far more than any other supernova type. The light curve is extremely broad. Rise to peak takes 100 to 200 days. The decline is shallow, powered by nickel decay for years. Peak luminosity reaches 10 to the 44 ergs per second. Pair instability supernovae require low metallicity. High metallicity stars lose too much mass through winds. They never reach the necessary core mass. Population 3 stars. The first stars in the universe are ideal candidates. Zero metallicity, masses reaching several hundred solar masses. Chemical evidence supports this. Research published in Nature in June 2023 reported Lamoste J1010 plus 2358, a halo star with abundance patterns matching a pair instability supernova, extremely low sodium. Large odd-even element variance. Comparison with models suggested a 260 solar mass progenitor. The star formed from gas, enriched by a PISN, first definitive association. However, follow-up work in April 2024 challenged this. High-resolution VLT spectra showed carbon and aluminum abundances too high for a pure PISN origin. Instead, a mixed model fit better. 13 solar mass core collapse supernova combined with a population 3 contribution. The story remains complex. Observed superluminous supernovae show PISN-like properties, but none confirmed. Supernova. 2018 IBB was a candidate. Extremely luminous, slow evolution, but detailed modeling suggested LBV-like eruption instead. The search continues. Research published in Monthly Notices in September 2024 calculated cosmic PISN rates. The maximum metallicity for PSN progenitors dominates uncertainty. If stars up to 0.006 solar metallicity explode as PSN rates are high. If limited to 0.001, rates drop 7 orders of magnitude. The main contribution comes from metallicities between 0.001 and 0.01, not pristine population 3 stars as often assumed. Pulsational pair instability, PPISN. For helium cores between 40 and 65 solar masses, pair production triggers pulsations instead of total disruption. The core contracts. Oxygen or silicon ignites. Energy release causes expansion. The star pulsates. Each pulse ejects mass. Shells of material fly outward. Eventually, the core mass drops below the instability threshold. Pulsations cease. The star settles. Later, it undergoes standard core collapse. a neutron star or black hole forms. The ejected shells create circumstellar material. When the final core collapse supernova occurs, the ejecta hits those shells. Interaction power is bright, long-duration transients. Some superluminous supernovae may be PPSN, followed by core collapse. The multipole structure creates complex light curves, early bumps, post-peak undulations. Research published in monthly notices in October 2023 modeled PPISN mass loss. Detailed simulations show stars lose 10 to 50 solar masses over multiple pulses. The pulses last seconds to hours. Time between pulses ranges from months to years. After several cycles, the core stabilizes. It evolves toward iron core formation, then collapses. The gravitational wave signal from the final black hole formation carries information about the pulsation history. The PPISN mass range creates a gap in black hole masses. Stars with helium cores between 40 and 65 solar masses lose mass through pulsations. The final black hole mass is lower than expected. This creates the pair instability mass gap. Black holes between roughly 50 and 120 solar masses should be rare. Observations from LIGO-Virgo gravitational wave detections show a feature around 35 solar masses, possibly the upper edge of the PPISN mass range. Electron capture supernovae, ECSN, stars with initial masses between 8 and 10 solar masses, develop degenerate oxygen-neon magnesium cores. As the core approaches the Chandrasekhar limit, densities reach levels where electrons are captured by neon-20 and magnesium-24 nuclei. Electron capture removes electron degeneracy pressure. The core collapses. A supernova results. But the mechanism differs from iron core collapse. Theory predicted this in 1980. 40 years passed before confirmation. Supernova, 2018, as D and NGC 2146 provided the evidence. Research published in Nature Astronomy in June 2021 analyzed 6 indicators. The pre-explosion images from Hubble showed a faint source consistent with a superasymptotic giant branch star, 8 to 9 solar masses. The circumstellar material showed unusual composition. Enhanced calcium and oxygen, low hydrogen. The explosion energy was weak, around 10 to the 50 ergs, 1/10 of typical core collapse. Little radioactive nickel, about 0.003 solar masses. The nebular spectrum showed strong calcium and oxygen emission. The combination is unique. Matches ECSN predictions perfectly. The distance to NGC 2146 is 31 million light-years, close enough for detailed study. The supernova peaked at magnitude -15, faint compared to typical type 2. The light curve showed a plateau lasting 60 days. Then rapid decline. Colors were bluer than normal, all consistent with ECSN models. This discovery potentially explains the Crab Nebula. Historical records from Chinese and Korean observers in 1054 AD describe a guest star visible in daylight. It faded over months. The remnant became the Crab Nebula. Spectroscopic analysis of Crab ejecta shows unusual abundances. Low iron, high oxygen, and neon, similar to SN 2018 ZD. The progenitor mass estimates for Crab are 8 to 10 solar masses. The explosion energy was weak. All indicators match electron capture. The mystery of the Crab may be solved. Electron capture supernovae produce low-mass neutron stars, around 1.2 to 1.3 solar masses. These neutron stars populate the lower end of the neutron star mass distribution. They are important for understanding binary evolution. NS plus He star systems can undergo ECSN. The second neutron star forms through electron capture. Double neutron star systems result. These systems eventually merge. Gravitational waves. Supernovae. The ECSN formation channel affects merger rates and properties. Hypernovae, collapsers, core collapse events with kinetic energies exceeding 10 to the 52 ergs, 10 times typical supernovae. Stars greater than 30 solar masses collapse to form black holes. If the star rotates rapidly, fallback material forms an accretion disk. The disk launches relativistic jets. The jets drill through the stellar envelope. They emerge. Gamma ray burst. The jets plow through material. Shockwaves. Nickel-56 synthesis. The visible supernova component. The combination is hypernova. Supernova, 1998, BW is the prototype. Discovered April 25, 1998 in ESO 184G82. Spatially and temporally coincident with gamma ray burst 98425. Spectrum showed broad lines. Expansion velocities exceeding 30,000 kilometers per second. 10% the speed of light. The light curve was broad. Peak luminosity 100 times typical type IBA. The nickel mass was around 0.5 solar masses. Enormous GRB 030329 provided conclusive proof. Detected March 29, 2003. Extremely bright. Optical afterglow followed. VLT spectra taken over 1 month showed spectral evolution. Early power law continuum, typical of GRB afterglow. By day 7, supernova features emerged. By day 20, dominated by supernova spectrum. SN 1998 BW-like. The connection between gamma-ray bursts and hypernovae confirmed. Research published in Nature in 2003 by the Grace collaboration established the collapsar model. Not all hypernovae produce observable gamma-ray bursts. The jet must break through the stellar envelope. If the star is too extended or the jet too weak, the jet stalls. Energy transfers to a cocoon. The cocoon absorbs the jet energy. No breakout, no gamma-ray burst. Research published in Nature in January 2019 showed this in GRB detected in December 2017. A dim GRB from a hypernova. The cocoon was detected. Hot, bright. The jet transferred too much energy to it. Barely emerged. The brightest gamma-ray burst ever recorded. GRB 221009A, detected October 9, 2022. Redshift 0.151, relatively nearby. The afterglow was bright enough for JWST spectroscopy. Observations taken at plus 168 days. Research published in Nature Astronomy in April 2024 confirmed a SN 1998 BW-like supernova. Nickel mass 0.09 solar masses. Slightly fainter than SN 1998 BW, but no R process signature. The expectation was that collapsars produce heavy elements through rapid neutron capture. The absence of R process emission suggests the mechanism is more complex. These events do not produce significant heavy elements. Neutron star mergers remain the dominant R process site. Colonovae, not supernovae, but related. Binary neutron star mergers or neutron star black hole mergers create colonovae. When two neutron stars spiral inward, gravitational wave emission drains orbital energy. They merge. A massive neutron star or black hole forms. Neutron-rich material ejects. Rapid neutron capture occurs. Heavy elements synthesize. Radioactive decay powers the kilonova, isotropic emission, visible for days to weeks. Luminosity around 1,000 times a nova, hence kilonova, GW1-70817, August 17, 2017. LIGO and Virgo detected gravitational waves from a binary neutron star merger in NGC 4993, distance 140 million light-years. The optical counterpart was at 2017 GFO, detected 11 hours post-merger. Multi-wavelength follow-up. UV to infrared. Spectra identified strontium and yttrium, conclusive R process evidence. The event confirmed that neutron star mergers produce heavy elements. The kilonova light curve evolved rapidly. Blue in the first day. Shifted to red. 2 components. Fast blue component from lanthanide-free ejecta, slow red component from lanthanide-rich material. The geometry was approximately spherical. Blackbody emission. Temperature dropped from 7,000 Kelvin to 3,000 over 2 weeks. GRB 230307A, detected February 2023, duration 200 seconds. Classified as long GRB, but the afterglow showed kilonova signature. JWST detected tellurium emission lines. Research published in February 2024 confirmed heavy element synthesis. The burst came from a neutron star merger. Not a collapsar. This challenges the long GRB paradigm. Neutron star mergers can produce long-duration bursts under certain conditions. Extended emission, magnetar central engine. Where are all the kilonovae? LIGO detected GW190425 in April 2019, a neutron star merger candidate. No electromagnetic counterpart found, despite extensive searches. The last confirmed kilonova was GW170817 in 2017, over 7 years ago. Observing Run 4 started May 2023. No detections yet. Expected to continue until June 2025. Astronomers are puzzled. Did we overestimate merger rates? Are electromagnetic counterparts weaker than predicted? Is viewing angle critical? Research published in November 2024 calculated detection probabilities for observing runs 4 and 5. The upgrades to LIGO Virgo Cagra will increase sensitivity. But the detection rate depends on kilonova brightness and search efficiency. If only 10% of mergers produce detectable kilonovae, we may wait years between events. Back to supernovae. The 8 major types: type Ia, thermonuclear, Type IB and IK, stripped envelope core collapse. Type 2, hydrogen-rich core collapse, including type 2 with interaction. Superluminous, type Y and 2. Extreme luminosity from magnetars or CSM interaction. Pair instability. Total disruption of massive low metallicity stars. Electron capture, weak explosions from intermediate mass stars. Hypernovae, collapsar black hole formation with relativistic jets. Each type writes a different story. Type IA map the universe. They measure cosmic acceleration. They reveal dark energy. Type IB and IK show us mass loss in binary systems, how stellar winds strip envelopes. Type 2 will illuminate the lives of red supergiants. Circumstellar interaction tells us about pre-explosion mass loss. Superluminous events push energy budgets to extremes. Magnetars, CSM interaction, rare progenitors, pair instability connects to the first stars, population 3 chemistry, the early universe. Electron capture fills the gap between white dwarfs and neutron stars, intermediate masses, degenerate cores, hypernovae tied to gamma ray bursts, relativistic jets, extreme rotation. If you value documented astronomical discovery and stellar death physics like this, subscribe. This is the kind of information we bring every time. Also comment from which city you're hearing this from. Now back to the information. The classification matters. Observers report supernova discoveries to the Transient Name Server. Over 19,000 objects reported in 2024. The Rochester Astronomical Society maintains statistics. 24,379 supernovae and transients listed for 2024. Of those, 1,533 confirmed type IA, 43 type IB, 70 type IK, 30 type SLS NI, 52 type TUN, 25 type 2IP, 40 type 2B. The sample grows every year. The Zwicky Transient Facility discovered 4,751 objects in 2024. Atlas discovered 3,242. Pan-STARRS discovered 7,135. The Vera Rubin Observatory will change everything. First light expected soon. Legacy survey of space and time will scan the entire visible sky every few nights. Tens of thousands of supernovae per year. The data volume will be massive. LSST will detect supernovae within hours of explosion, early spectra, pre-maximum observations, the physics of shock breakout, flash spectroscopy. We will see stars explode in real time. Supernova 2008D demonstrated this. Detected January 9, 2008 in NGC 2770. Swift satellite caught the X-ray flash from shock breakout. The moment the shock wave erupted through the stellar surface, X-rays dominated for minutes, then optical brightening. The earliest observations ever, the progenitor was likely a Wolf-Rayet star, compact, dense, fast shock transit. Shock breakout physics is complex. The shock wave accelerates through decreasing density, reaches the surface, temperature spikes, photons decouple, radiation escapes. The duration depends on progenitor radius. Compact stars flash briefly. Extended stars take hours. If the spectrum is hot, UV dominant, then cools rapidly. Catch it early or miss it. Future surveys will find hundreds of shock breakouts per year. LSST, Roman Space Telescope, high cadence monitoring. Multi-wavelength coordination. The observational landscape is changing. 20 years ago, we detected dozens of supernovae annually. Now thousands, soon tens of thousands. The statistics will be robust. Rare subtypes will become common. Electron capture supernovae, pair instability candidates. Every variant will have samples. The most distant supernova ever observed, Assassin 15 LH, redshift 0.23, distance 3.82 gigalight years, peak absolute magnitude minus 23.5, 100 times more luminous than superluminous supernovae. The nature remains debated, initially classified as SLSNI. Later analysis suggested tidal disruption event, a star shredded by a supermassive black hole. The accretion flare mimics a supernova. The light curve does not match standard models. Too bright, too long, the mystery persists. Supernova 2025 when just discovered. Redshift 2.011, a type starting superluminous supernova. Strongly gravitationally lensed, 4 images resolved. Angular separation 1.7 arc seconds. Magnification factor 20 to 50. Research published in October 2025 confirmed spectroscopic classification, broad absorption features, carbon, magnesium, silicon, titanium, iron, matches SLS and I. The first confirmed gravitationally lensed superluminous supernova. The magnification allows detailed study, spectra at phases impossible for unlensed events. The early UV luminosity is extreme, either intrinsically overluminous or caught at very early times. Future monitoring will distinguish. The diversity is staggering. Type Ia with smooth light curves or bumps, type Ike with gamma ray bursts or without, type 2 with plateaus or linear declines, superluminous events with magnetar power or interaction power, pair instability or pulsational, electron capture or iron core collapse, hypernovae with jets or cocoons. Colonnovae from NS-NS or NSBH mergers, but patterns emerge. Low metallicity environments favor superluminous and pair instability events. High rotation produces magnetars and hypernovae. Binary interaction strips envelopes and creates type IB and IC. Circumstellar material creates interaction-powered transients. Mass and composition determine the mechanism. 8 to 10 solar masses give electron capture. 10 to 25 give standard core collapse. 25 to 50 give hypernovae. Over 130 give pair instability. The remnants matter. Type Ia leave nothing. Completely dispersed. Type IB, Ike. 2. Leave neutron stars or black holes. Electron capture leaves low-mass neutron stars. Hypernovae leave black holes. Pair instability leaves nothing. The neutron star mass function shows peaks. 1.3 solar masses. 1.8 solar masses. The distribution connects to progenitor types. Electron capture produces the low-mass peak. Standard core collapse produces the high-mass peak. Gravitational waves from supernova core collapse are weak. LIGO cannot detect them beyond the local group, but future detectors may. Einstein telescope, Cosmic Explorer, sensitivities 100 times better. Core collapse signals will become routine. Bounce, ring down, prompt collapse, fallback accretion. Each mechanism has a signature. Neutrinos carry most of the energy. Supernova 1987A in the Large Magellanic Cloud, February 23, 1987. Kamiokande detected 11 neutrinos. IMB detected 8. The burst lasted 13 seconds. Total energy 10 to the 53 ergs. 99% neutrinos, 1% kinetic. The neutrino signal preceded the optical brightening by 3 hours. Core collapse happened first. Shockwave took time to reach the surface. That is normal. IceCube searches for high-energy neutrinos from supernovae, TeV to PeV range. Core collapse events may produce them through cosmic ray acceleration. Type Dow and supernovae with dense CSM are promising proton acceleration in shocks, hadronic interactions, pion decay, neutrinos. Research published in August 2025 searched for IceCube alerts coincident with type Titaurun supernovae. 2 candidates found, SN 2023 SYZ and SN 2025 CBJ, spatially and temporally consistent. Significance marginal. Future searches will accumulate statistics. The chemical enrichment story is profound. Supernovae produce elements, oxygen, silicon, calcium, iron, nickel. Every atom heavier than helium comes from stars or supernovae. Type Ia produce iron peak elements. Type 2 produce oxygen and silicon. Hypernovae may produce lighter R process. Kilinovae produce heavy R process. Gold, platinum, uranium. Your body contains atoms from supernovae, carbon, nitrogen, oxygen, iron in your blood, calcium in your bones, zinc in your enzymes. All forged in stellar cores, all ejected in explosions. The universe recycles. Gas, stars. Supernovae, gas again. The interstellar medium is enriched with each generation. First stars were pure hydrogen and helium. Second generation had trace metals. Third generation more. Now the sun is roughly 2% metals, sufficient to build planets. Life requires metals, carbon, oxygen, nitrogen, phosphorus. Without supernovae, no rocky planets. No biochemistry, no observers. Type Ia inject iron, about 0.6 solar masses per event, but they destroy white dwarfs, remove mass from the stellar population. Type 2 inject oxygen, about 1 solar mass per event. Type IB and Ike inject helium and heavy elements. Hypernovae inject even more. The mix matters. Galactic chemical evolution models track element ratios over time, iron to hydrogen, oxygen to iron, alpha element enhancement. The data constrains supernova rates and yields. Dust formation happens in supernova ejecta. Months to years after explosion, the gas cools, condenses, silicates, graphite, iron grains. Supernova 1987, A produced dust. Observations 10 years post-explosion detected infrared excess. Warm dust, half a solar mass estimated. Dust is crucial. It absorbs starlight, re-radiates in infrared, cools molecular clouds, enables star formation. The cycle continues. The observational campaigns are intense. Transient surveys, spectroscopic follow-up, multi-wavelength monitoring, coordinated efforts. The Global Supernova Project at Las Cumbres Observatory uses a network of robotic telescopes worldwide. Observations within hours. Multiband photometry, spectra from Gemini, Keck, VLT. The data feeds into the Open Supernova Catalog, the Weisman Interactive Supernova Data Repository, WISE-REP, thousands of spectra, hundreds of light curves. Public access. The community shares data. The modeling is sophisticated. One-dimensional radiative transfer. Stella code, CMF-GEN, three-dimensional hydrodynamics. Flash, Castro, neutrino transport, Boltzmann solvers. The simulations reproduce observations, fit light curves, extract parameters, progenitor mass, explosion energy, nickel mass. The models constrain physics, equation of state and neutrino cross-sections, mixing. The interplay between theory and observation is tight. Citizen scientists contribute. The Zooniverse projects, supernova hunters, amateur astronomers discover transients, backyard telescopes, CCD cameras, online submission. Koichi Itagaki in Japan has discovered hundreds of supernovae. Visual patrols, his discoveries contribute to science. The community is global, professional, amateur, collaborative. The future is bright. LSST begins soon. Roman Space Telescope launches. JWST observes distant events. Extremely large telescopes under construction. Gravitational wave detectors upgrade. Neutrino experiments expand. The next decade will rewrite supernova astrophysics. We will see the first stars explode. Pair instability supernovae at redshift 10, population 3 signatures. We will watch stars explode in real time. Shock breakout, early spectra. We will detect gravitational waves from core collapse. Neutrino signals, multi-messenger astronomy. Supernovae are not just explosions. They are laboratories, extreme physics, nuclear reactions at billions of Kelvin, densities exceeding nuclear matter, magnetic fields, trillions of Gauss. Relativistic jets, gravitational collapse, quantum degeneracy, neutrino transport. Every aspect pushes the boundaries of physics, and they are clocks. Type IA measure distances, map expansion history, constrain dark energy. The equation of state, supernova cosmology, earned the Nobel Prize. The discovery of accelerating expansion. Dark energy dominates the universe, 70% of the total energy density. We do not know what it is. Supernovae revealed it. They are also dangers. A nearby supernova could sterilize Earth. The radiation, cosmic rays, gamma rays. Within 10 parsecs would be catastrophic. Within 30 parsecs damaging. The last nearby supernova was Vela. 11,000 years ago, 800 light years, harmless. Betelgeuse will go eventually, 600 light years, safe distance. The show will be spectacular, bright as the moon, visible in daylight, last for months, then fade. Leave a nebula, a neutron star. We wait. The oldest known supernova remnant is RxJ 0852.0-4622, age estimated from temperature measurements, and titanium-44 gamma ray decay. About 800 to 1,000 years. The event was not recorded, too faint or obscured, but the remnant remains. Cassiopeia A, young remnant. Age estimated from light echoes, about 340 years. Exploded around 1680. No historical records, perhaps because of dust extinction. The light was blocked. The remnant is bright in X-rays. Chandra observes it frequently. The ejecta structure, asymmetries, clumps, fast-moving knots. Reverse shock, forward shock, the neutron star at the center, detected in X-rays, cooling rapidly. The data constrain neutron star cooling models, equation of state, superfluidity, exotic matter, the Crab Nebula, 1054 supernova, still expanding. The pulsar at the center spins 30 times per second, powers the nebula, synchrotron radiation, gamma rays to radio. The Wind Nebula glows. The filaments trace the original explosion. Composition, velocity. Each knot tells a story. Supernova remnants fade over tens of thousands of years. The shockwave slows, radiative cooling increases, eventually merges with the interstellar medium, disappears. The cycle completes. The enriched gas forms new stars. Some of those stars explode. The process repeats. galactic recycling. 8 types. Type Ia, Ib, Ek, 2, including IIN, IIP, IIB, SLSNI, SLSN2, Pisn, ECSN, Hypernovae, each one unique. Each one revealing something about the universe, the physics of matter under extreme conditions, the life and death of stars, the origin of elements, the expansion of space, the fate of galaxies. Stars die. We now know how. 8 ways to collapse, explode, shine. And every one of them changes the cosmos, every atom, every galaxy, every planet. Supernova remnants excavated in Australia show our process elements deposited on Earth, traces in ancient seabed. Plutonium-244, live radioactive isotopes from nearby supernova 2 million years ago. The evidence is beneath our feet. Final data point. A soil core from Antarctica. Analysis published, showing traces of iron-60, radioactive iron from supernova fallout, deposited in ice. The isotope has a half-life of 2.6 million years. Terrestrial sources are extinct. The only explanation is extraterrestrial. Supernova debris rained down. The local bubble formed from multiple supernovae. 10 to 20 events, 5 to 15 million years ago. We live inside the cavity. Low-density hot plasma. The sun happened to be passing through. Lucky timing, or we would not exist. The universe makes stars. Stars make elements. Supernovae scatter them. New stars form. The cycle continues. Entropy increases. Complexity emerges. Eventually, observers arise. We are made of stardust, not metaphorically, literally. Supernova nucleosynthesis. The chain of causation runs from the first stars to you reading this. Every carbon atom in your DNA forged in a star, ejected in a supernova, billions of years ago. Now assembled into something that can contemplate its own origin. 8 types of supernova, 8 ways the universe builds elements, 8 mechanisms to end a star. And every single one tells us we are connected to the cosmos in the most direct way possible.